So in the previous video, we saw that the SGD updates are noisy as compared to GD updates or gradient descent based updates. Basically, the derivatives or gradients that we compute using SGD are noisy because they're approximations to the gradient descent derivatives, right? So we said, can we somehow denoise this data? Let's understand a very, very simple concept of denoising. Very, very simple concept. Imagine if you give me a bunch of numbers, let's say A1, A2, A3, A4, A5, A6, so on and so forth. Suppose you give me a bunch of numbers and you tell me, okay, let's assume this happens at time equals to 1. Suppose this is a value that I get at time equals to 1. This is a value that I get at time equals to t, time equals to 3, time equals to 4, so on and so forth. One simple way of denoising is to take averages. Very, very simple concept is to take averages. Right? And the way it works is this. I can simply say that at V1, so I'll simply say at V1 I don't have much data. Right? At time equals to 1, I don't have much data, I have only 1 point. So I'll call my V1 equals to A1. But for V2, I will say that I have my V1. Right? I already have my V1, right? So can I say that I'll take some gamma times V1 plus V2? When I do this, let's assume gamma equals to 1. Let's assume gamma equals to 1. Then my V2, sorry, this is A2, I'm sorry, this is A2. So at t equals to 1, I have only one value, which is A1. So I'll just use that value. At t equals to 2, I have two values. I've already seen A1 and I'm seeing A2. So what if I write an equation like this where I say that gamma lies between 0 and 1? Right? Let's say I write this equation saying gamma lies between 0 and 1. If gamma equals to 1, what happens? If gamma equals to 1, my V2 equals to V1 plus A2. What is V1? It is nothing but A1 plus A2. If gamma equals to 1, my V2 is equals to A1 plus A2. What happens if my gamma equals to 0? Then my V2 equals to 0 times V1 plus A2, which is equal to A2. What happens if my gamma equals to 0.5? Okay, what happens if my gamma equals to 0.5? Then my V2 becomes 0.5 times V1 plus A2, which is equal to 0.5 times A1 plus A2. So what I'm saying here is I will give, so this is, you can think of this like a weighted sum, right? Where you're giving more weightage of 1 to the most recent point you have seen and less weightage to a point that you have seen in the past, right? So let's just extend this, right? So V1 equals to A1, V2 equals to gamma times V1 plus A2. Let's say V3. V3 is what? Gamma times V2 plus A3. So let's expand this. What does gamma times V2 mean? It means gamma times, what is V2? V2 is gamma times V1 plus A2 plus A3. So what does this mean? It means gamma square V1 plus gamma square A2 plus A3. If you think about it, remember, gamma lies between 0 and 1, right? So here you have a value of 1 into A3. So look at it. This is 1 into A3. This is something less than 1 into A2. And gamma square, because let's say gamma equals to 0.5. Let's just say. Then I can write this as, what is gamma square? 0.25 V1, 0.25 A1, sorry. 0.25 A1, because V1 equals to A1, right? So 0.25 A1 plus 0.5 A2 plus 1 times A3. So at t equals to 3, I have seen a value A3 and hence I'm giving more weightage to this. I'm giving lesser weightage to the previous point that I've seen because I've seen this point at t equals to 3. I've seen this point at t equals to 2. I've seen this point at t equals to 1. So the most recent point I've seen, I'm giving it more weight. The next recent point, I'm giving it lesser weight. The next point, I'm giving still lesser weight. Okay. So now what happens at V4? V4 can be written as, right? V4 can be written as 0.125 times A1 plus 0.25 times A2 plus 0.5 times A3 plus A4. See, I'm giving most weightage to A4, lesser weightage to A3, still lesser to A2, still lesser to A1. So if you employ this function, okay, let me write this function. This function is as follows. V1 equals to A1 and V at any time t is gamma times V at t minus 1 plus A at time t. These are called recursive equations. These are called recursive equations in computer science because you're representing, right? Or you can think of it as time-based, or it's easier to think this way. It's easier to think of this from a programming perspective. V is a variable that changes over time, right? And Vt minus 1 is the value that you have at previous time. Now, as you're getting more and more data, right? As you're getting more and more data with time, this is a t equals to 1, time equals to 1, second step, third time, fourth time, fifth time, sixth time, etc. Okay, by performing this, you're sort of performing like an averaging, like a denoising. Okay, by performing this, V at any time t can be thought of as a denoised estimate, where you're giving most weightage to the most recent point and you're giving lesser and lesser weightages to previous data points. In this video, I've provided you a very nice reference link from Towards Data Science. Very, very nice example to understand this better. So let me explain this. Okay. So you have some data here. Okay. Each of these is a data point. Each of these blue dots is some data. Remember, the data is very noisy. The original function looks like this red line. This red line that I'm highlighting right now, right? This red line here is the original function. This is the original data. This is like our derivative when you compute using gradient descent, which is the original. The blue ones are the noisy data. So you can think of these blue ones as the derivatives that we got using SGD, right? So the blue ones are very noisy. So one way to clean up this noise is something called as exponentially weighted averages, which is exactly what we saw right now. Because if you look at it, it's called exponentially weighted averages because if you think about it, V at any time t is 1 times A at time t plus gamma times A at t minus 1 plus gamma square times A at t minus 3 plus gamma cube times A at t minus 4 plus gamma 4 times A at t minus 5 and so on and so forth. You are giving a weightage of 1 to the most recent point, gamma weightage of gamma to the second most recent point, gamma square to the third recent point, gamma cube to the fourth recent point, gamma to the power of 4. So exponentially you're increasing or you're reducing these weights because your gamma lies between 0 and 1, right? So gamma is greater than 1 is greater than gamma, greater than equal to, and gamma is certainly greater than gamma square, which is greater than gamma cube, which is greater than gamma 4, which is greater than gamma 5, and so on and so forth. And exponentially you're giving weights in such a way that this is gamma power 1. This you can think of it as gamma power 0, right? Because what is gamma power 0? It is equal to 1. So this is gamma power 0, gamma power 1, gamma power 2, 3, 4, so on and so forth, right? So this is called exponential weighted averages, or in this case exponential weighted sums, because you're just summing it up here, right? Very interesting concept. So for this data, imagine that this is the original function. The red line is the original function. The blue dots is the noisy data that you have sampled. If you apply the exponential moving average, which means at this point you'll say to predict what is the value here. Okay, so let me just erase this just for clarity. Suppose you're here, you want to predict what is the value here. So you take the value that you saw here, which is your A at this point. So this is your AT. See the previous value, which is AT minus 1. See the previous value, AT minus 2. If you apply this form of formulation, which is called exponential moving average or exponential weighting average, I'm sorry, if you call this as, if you're applying exponentially weighted averages, what happens is the value that you get here is this yellow line. You see this yellow line here, right? This yellow line is what you will get if you apply exponentially weighted averages. Now, if you notice this yellow line, is a very good approximation to the red line as compared to the blue points. This is a much better approximation than the blue points. Blue points are a much more noisy approximation to the red. If I just combine the blue lines, okay, just look at this. If I just keep combining the blue lines, the curve that I'll get is like this. Very, very noisy curve. But by just doing this exponential weighted averages, right, I'm getting a much more smoother curve, which is your yellow line, right? So this is how you can denoise data. So you can denoise data. So the core idea is you can denoise data, especially when you have very noisy data. You can denoise it using exponential weighting. Exponential weighting or exponential weighing. Weighting is the wrong word here. Weighting is this. This is weighting. This is weighing. Okay. So you can denoise this using this. So let's take this concept of denoising data using exponential weighing back to our SGD. Right? So what is our initial update? Our initial update is, or what is our mini batch SGD update? Our mini batch SGD update is weight at time t, or with a tth iteration, is the weights at t minus 1th iteration minus eta times the derivative of this, the derivative with respect to wt minus 1. Okay, let's introduce some more simple notation here. Instead of writing this all the time, because this is cumbersome to write, let's call this as GT, gradient at time t. Okay, so gradient at time t is derivative of your loss function with respect to w, but computed at t minus 1th step. This is very important. Let's define this. Let's define. So just for notation, just to simplify notation, let's write this. What is this? This is a gradient of the loss function with respect to w, right, at point wt minus 1. But this gradient is computed at the tth step to update at the tth iteration or the tth step in the iteration. Okay. So if you define this as this, you can write your weight wt as wt minus 1 minus eta times gt. Much more easy thing to read, right? See, we are simplifying the notation as we go. Because what is gt? This is very important. gt is the gradient which is contributing to the tth iteration, which is nothing but derivative of L with respect to the weight at t minus 1th point, right? Okay, so this is our simple mini batch SGD, right? When I compute this gradient, remember this gradient I'm computing using mini batch SGD. Okay, because we can't compute it using simple SGD or simple GD, sorry, full GD with all the points. So whenever I say GT, I'm assuming that this is computed using mini batch SGD. I'm assuming that by default. Okay. Okay. Having said that, this is your update equation. This is your standard update equation in mini batch SGD. Now we'll modify this. We'll modify this using our exponential weighing. Using our exponential weighing concept. We'll change this slightly. Okay. Let me write the equation here. I will define Vt as gamma times Vt minus 1 plus eta times Gt. Okay, let me just write it. I'll explain this in more detail for you. And I'll define Wt as Wt minus 1 minus Vt. Okay, now let's go and understand this. Okay, what happens? Let's write case by case. Case 1. If my gamma equals to 0. Okay, if my gamma equals to 0. Again, I'm defining, so let me just write it. Let me just define my V1 as V1, because this is a time t, right? You have to define V1 somewhere. At the first iteration, what is your V value? The first iteration, your V value is just this. That's it. G1. Okay, so let me write it as G1. Gradient in the first iteration, eta into gradient at the first iteration. Okay, this is how I define this. Is, if you look at this, this is exactly like my exponential weighing, right? Instead of ATs here, I'm writing eta times G1. Eta is my learning rate. Okay. What happens if my gamma equals to 0 here? If gamma equals to 0, okay, at any time Vt is going to be eta times Gt, which implies, what is my Wt? My Wt is Wt minus 1 minus eta times Gt. This is nothing but your simple update, right? If gamma equals to 0, what you have is your simple case. Very, very simple case. Okay. Typically, we have our gamma lying between 0 and 1. A good value for gamma that people often use is 0.9 in practice. In practice, people typically use gamma as 0.9. Right? So this whole thing that we have, let's assume my case 2. Okay, if gamma equals to 0.9, then what do I have? I have my Vt as 0.9 times Vt minus 1 plus my learning rate times Gt, and what is my Wt now? My Wt equals to Wt minus 1 minus 0.9 times my Vt minus 1 plus eta times Gt. So if you compare this with this, okay, or if you compare, because this is same as this, if you compare this and this, the only new term that you have is this, except that you have your Wt minus 1 here, Wt minus 1 here, you have minus of eta Gt, you have minus of eta Gt here. The only new term is this. Okay, so when you use exponential weighing to denoise your gradients, so the core idea is this: when you use exponential weighing to denoise your SGD gradients, right? What you get here is nothing but SGD plus momentum. What you get here is called SGD plus momentum. And this term here is called the momentum term. Right? This term here, this is your standard gradient term, right? This is your standard gradient. So in this whole equation, if you think about it, so let's write this down, right? So if you write it down in one term here, what you get here is this: Wt equals to Wt minus 1 minus, right, eta times Vt, right, Vt minus 1, sorry, Vt minus 1, right, Vt minus 1 plus eta times Gt. Now if you think about it, this is your gradient term, right? This is your gradient term. This term is called the momentum term. This term is called the momentum term. Because think about like this: momentum is computed using all the previous values, right? Using Gt minus 1, Gt minus 2, Gt minus 3, Gt minus 4. I'm using all of these values. Literally in Vt minus 1, I have all of these values inherently, right? All of these values are already present in this. Because look at the definition. Through this definition, just like in the case of A1, A2 that we have seen, this data is already present. So in your Vt is what? Your Vt is eta times Gt. Okay, so let me write it down just for your clarity, just so that you understand it better. Your Vt is 1 into eta times Gt plus gamma times eta times Gt minus 1 plus gamma square times eta times Gt minus 2 plus gamma cube eta times Gt minus 3, so on and so forth. So you have one gamma square, gamma cube, so on and so forth. But you have Gt here, you have Gt minus 1, Gt minus 2, Gt minus 3. All the previous values are here. It's called momentum because you're taking all the previous values to compute it, to gain some momentum. Okay, through your exponential weighing. Right? So geometrically speaking. So this is the mathematical part. And why are we doing all of this? The core concept is we are using exponential weighing to denoise our SGD gradients. Now what happens geometrically is, suppose you're at this point. So let's assume this is at Wt. You're at the Tth iteration. You're at this point, let's say. Okay, suppose you're at this point. Now what happens is your gradient will say move in this direction. Your gradient. What is your gradient? Your gradient is eta times gt. So minus eta times gt will say move in this direction, because you go in the negative direction of the gradient, right? Okay, your gradient says go in this direction. Your momentum says go in this direction. Your momentum, what is your momentum? Your momentum is coming because of your gamma Vt minus 1, the negative of this, obviously. Okay, so your momentum says go in this direction, your gradient says go in this direction. And what are you doing here? You are saying Wt equals to Wt minus 1. You can think of it as plus minus gradient this. See, I've taken this minus sign inside, literally, right? Minus eta times gt. In this update equation, if you take the negative sign inside, the negative comes here, the positives come out, right? So what am I doing here? I'm taking my previous value. Okay, so let's say this is Wt minus 1. My new Wt is old Wt minus 1 plus the sum of both these gradients. Both these vectors. So if my Wt minus 1 is here, let's say this is t minus 1, just for simplicity. This is my Wt minus 1. If my gradient says go this direction, if my momentum says go this direction, eventually I'll go in this direction. And what is this direction? This direction is, and eventually I will land up here. And what is this? This is my Wt. So whenever I'm making a move, okay, let's go back to the diagram that we saw. Okay, let's go back to the diagram that we have seen. Okay, let me just open it for you. Let's go to images.google.com, and it's very simple. Just say SGD convergence. Okay, Google will type correct for you. Okay, this is the diagram that we saw in the previous video, right? If simple SGD is taking you down this path, first path, second path, third path, etc., what happens in SGD with momentum is this. Because in the past you have gone in these directions, it will accumulate all of that information. Okay, so in this video, and it'll move faster. Let me explain you why. So in this video, in the description section, I've provided you a brilliant reference for all of these algorithms by a phenomenal writer called Sebastian Ruder. This is one of the best blogs I've seen explaining all of these optimization algorithms in very good detail, right? If your simple SGD makes these steps, it goes up here. Suppose we have to finally reach here, right? Suppose this is my starting point, it goes up, comes down, it does this. But what happens in SGD with momentum is, first steps will always be same. But eventually, it knows that because I'm doing this back and forth, your algorithm eventually knows that the final direction that I'm going is this direction, towards this. So it will start making longer steps. It will start making longer steps towards the minima that we care about, because we are computing this momentum. Please note that some of the notation here is slightly different. This basically, this part here basically means derivative. It's basically the grad symbol that we saw in the optimization. This is the grad thing. This is the grad notation instead of the partial derivative notation, except that the core concept is the same. Okay, so in a nutshell, SGD with momentum, the most important idea, the most important reason why we learn this is SGD plus momentum will speed up your convergence, dramatically. This is a very, very important idea in the whole of optimization. As important as the idea of SGD is, equally important is the idea of momentum. Very, very important concept. And hence I've taken a lot of time to explain this in detail. It's a very, very important concept. Then some of the next concepts that we learn are just improvements on this. Small improvements on this, nothing very fancy. But the core idea that we saw here, the core concept that we saw here of using momentum or using exponential weighing or exponential weighing is a very, very important concept in the whole of optimization.